Okay, so I'm going to talk a bit about OneFS, and since there's a lot of people not very familiar with Isilon, I'll cover that in a little more depth, particularly on this slide. And I want to talk about OneFS, which is effectively our software, and some of what we had to do to make it work effectively in an all-flash system. So, like a lot of storage companies, we're based around FreeBSD at the kernel layer. We have a pretty heavily modified version of FreeBSD that we use. We have a group of engineers that is dedicated to maintaining that operating system for us. And we've also been pushing back our changes when they make sense to the broader community into the FreeBSD head. Some of the sort of changes that we do there are purely performance improvements, but then we also have a lot of changes at the VFS, the operating system file interface, to support the fact that we're clustered effectively, because we're using FreeBSD as not only the kernel, but we also are a FreeBSD file system. So FreeBSD applications can effectively just see us through a POSIX interface. That's important because our protocol heads, that's what we call the software that receives requests from the client and processes them. So NFS, SMB CIFS, Swift, REST APIs, FTP, and so forth are all in user space, and that allows us to, for instance, if we have a new protocol coming in, we can start with an initial, say, standard FTP server, and that just works because the file system looks like a standard POSIX file system under the covers. And then for the protocols where performance is more important, like NFS, SMB, HDFS, we'll build a custom protocol head that takes advantage of a lot of the changes that we've made at the file system layer to do things like zero copy, so that we don't need to move data between the network user space and back into the kernel for the file system. Effectively, when we get an NFS request, for example, the user space only looks at enough to see what the request is and then passes the data from the network socket to the file system without ever moving it into user space. The file system is in the kernel. That's different than a lot of scale-out storage companies, and that's primarily because by keeping it in the kernel, we have a single address space and we've got higher performance. When we don't have to cross a user kernel barrier to get to a device driver, we don't have to cross user kernel barriers to do our RPC between nodes and so forth. Putting it in the kernel and requiring that most of our user space code be able to get to all of our new features required that we add a lot of enhancements to maintain the efficiency. For instance, NFS a lot of read and write requests that come in over NFS have pre and post attributes that go with them that helps the client maintain consistency. And so we have APIs that return back that extra information. And I listed a few examples there. We have optimizations to support the reader plus in NFS. We support the Windows ACLs natively. We support being able to effectively do an fsync on just a portion of a file, which is important for NFS commit operations. And then for the clustering, we have a RPC mechanism that goes between nodes that goes over the backend network. For InfiniBand, we built that on SDP, Socket Direct Protocol, which effectively provides you Unix sockets over InfiniBand. So we're not taking advantage of the verbs, but that allows us to swap out easily to Ethernet without any changes to the upper level software. So we just use TCP, and a bit of a caveat on that I'll get to in a later slide. We have a distributed lock manager. We are fully symmetric, as John pointed out, so there's no notion of a node that owns a particular file or owns a particular directory. We are a single volume across the whole cluster, not just from the outside world, but internally. And the DLM is key to making all of that work. We use a transactional disk update model. So a write operation to complete needs to have its data committed on all of the nodes in the cluster that participate in that write. And technically, it's all of the nodes less one, so that we're non-blocking in the event of a failed node. We don't have to wait to make a decision if a node is really down or not before we can complete transactions, which is important to keep the client latency low in the event of failures. And our transactions are a little different, and this is related to the fact that we're scale out. Most file system journals are at a logical level. So create this entry, write this data to this logical block of a file. Our journals are at a physical layer. That allows the journal to be resident only, well, it does two things. First of all, it eliminates contention between nodes, because that's all being dealt with at the lock manager, the DLM layer. If I have a lock on a file or a range of a file data, then I know I'm not going to have any contention writing to the journal. And the second thing is that it means that when a node crashes and comes back, it can replay the journal without having to involve any other nodes. It can replay its journal, know it's at a consistent state with respect to the rest of the cluster, and then rejoin the cluster. We have a large journal in main memory, and I'll talk a little bit more about why that's important later.
Did you say a write has to be acknowledged by all the nodes in the system, or all the nodes participating in the data placement?
All the nodes participating in the placement of that write. Okay. So if it's spread across 8 nodes, then 7 at least of those nodes have to respond back.
And the protection capability is mirroring or RAID, or?
We support a variety. Generally, what we recommend is that customers use the Reed-Solomon encoding, and we support up to a 16+4 encoding. So that would be 16 data nodes and tolerant of 4 failures. And we also support mirroring. Metadata in the system is mirrored. We can mirror actually up to 8x, and users can request that if they want to be extremely fault tolerant. We do that for some of our internal data structures that are critical to the file system.
What's the size of your file? Size of your file system? I mean, you mentioned that there's one volume across the whole cluster, but that's multiple file systems, I guess?
One file system.
One file system.
So 33 petabytes at the moment would be our
What's the size of the max size of the file?
For a file,
the max size is 4 terabytes today.
4 terabytes.
Yeah.
We're working.
We have a project to bump that up to support a single file across the whole thing. So when we decided that we were going to build a flash optimized version of this, on the software side, we had to take a hard look at our software and decide where are we going to invest the effort to make things faster. Because we are file-based, that means that we have sort of by default a lot of overhead compared to a block-based system. The translation is more complicated. We support much more complex operations coming in from clients, and so we spend a lot of CPU to deal with things like ECC and so forth. And that matters a lot more when you have flash, if you want to take advantage of the flash, because if you're getting 100,000 operations per second out of your flash drive, that's roughly on the order of 20,000 CPU cycles per operation. And if you're taking much more than that, then you're worse than doubling the overhead of going out to disk. Memory bandwidth became an issue for us. It hasn't been as much of an issue for us in the past, just because we can push more data through the system, and DRAM bandwidth in and out of DRAM started becoming more of an issue than it had been in the past. Network bandwidth and latency are pretty much our major bottlenecks today, so we did as much as we could to improve that, but to be honest, 40 gigabit link is going to be a bottleneck if you're talking to 60 SSDs or even 15 SSDs. Our disk subsystem, SSDs work much better if you can give them enough parallelism to keep all of the dies busy, and it's pretty hard to build up a big enough queue with the default scheduler that we had. We also found that on a lot of the SSDs we tested, alternating reads and writes led to fairly poor performance. And I think part of that is the controller in the SSDs. Part of that is the way that the flash dies themselves are optimized. So we needed to do a better job of grouping reads together, grouping writes together. That's part of where having a large journal comes in, is it allows us to do a better job there. Sorting operations is very helpful for hard drives, and it's not very helpful for SSDs, and it can be harmful because you can just spend so many CPU cycles sorting things that are going to run at the same speed, whether you sort them or not. The only case where it's useful is if we can sort of opportunistically take a bunch of contiguous small IOs and turn them into one large IO, and that's a useful thing. So we still do that. The operating system, we're in FreeBSD. It's got latency with thread switching, with the buffer cache, memory management, and there were several areas there where we could measure that there were problems once we started putting faster flashes in. And then lock contention became more of an issue for us because to drive SSDs at full rate, we needed faster CPUs with more cores, and all of a sudden locks that were not heavily contended at 16 threads accessing them became a bottleneck when we had 32 threads that were all trying to get at them at once. And here I'm talking primarily about the locks on a single node. The contention between nodes for a distributed lock manager, to be honest, didn't really change much. So what did we do to make it faster? First of all, we started by improving our in-house profiling tools. We also updated some of the profiling tools that were in FreeBSD. We used some third-party profilers. And we found areas in the FreeBSD kernel, in the file system, and in our user space that we were spending a lot of CPU, and we looked at each of those to see where we could improve it, and I've got some examples of that on the next slide. The network stack, on the front end, we basically took advantage of what had been done in the FreeBSD community already. We talked to some other large companies that use FreeBSD for network-heavy applications and got some of their improvements and incorporated them in. We had a couple of other problems still. One is that on the back end, with InfiniBand, we never really had to deal with an incast problem because the credit mechanism on InfiniBand deals with that very well. And some of you may not be familiar with incast since it's more of a networking and HPC problem than a storage problem, but effectively, if I've got a client that's reading a file at full rate, and we're spreading the data for that file across 16 nodes, I may send 16 read requests to those nodes to get a block out, and all 16 of those nodes are going to throw the data back at me on the back end at the same time. And if I have one 40 gig network port that I'm pulling that data in, and I'm talking to 16 nodes that are throwing data out, each at 40 gigabits, then that's going to collide on the network. TCP is going to say, oh, things are congested, I need to start backing off. And now all of a sudden my, say, 50 microsecond latency to get data from another node is becoming like single to tens to even hundreds of milliseconds of latency as TCP decides even more aggressively, I need to back off more, it's still congested. So we adopted, people have looked at this obviously in the past, we adopted data center TCP. There was some support for this in FreeBSD. That uses a mechanism called explicit congestion notifications. So when a port starts getting busy, it starts responding back to other people talking to it and saying, hey, I'm getting busy, pause for a little bit, and I'll tell you when it's okay to transmit again. So there was some support for that in FreeBSD. We fixed some bugs in it, enhanced it a bit. We decided that we needed higher frequency timers as well. The TCP retransmit timers were just not fast enough to recover from an incast without introducing unacceptable latency for us. So we made the timers faster, we increased the clock tick rate, and we added some algorithms for retransmission that were tuned to the particular problems that we had, which are very bursty behavior, where the total amount of data coming into the port is never going to really exceed the amount that a client's asking for. But it's very bursty because we're prefetching data, because we're completing a read and pushing all of the data for that read at once. And then the other thing that we found is, in the FreeBSD side, on the front-end side, is that FreeBSD did a wonderful job of keeping a 40 gigabit link busy with hundreds of clients reading from it. If we put 1 or 2 clients on it, it didn't. And after investigating that for a while, what we found was that the TCP stack sort of had a top end, which was pushing data into the socket, and a bottom end, which was getting data out of the socket, and a lock in between those. And that lock became too contended if we were trying to push data at 30 or 40 gigabits per second through the socket. And so we rewrote some of the transmission code to hold the lock for less time on both of those ends, and we're able to get to the point where with 2 clients we can saturate the 40 gigabit link. And I believe that change is going into FreeBSD sometime soon. We rewrote the I/O scheduler. It's much more aggressive now at grouping reads and writes together. Generally, we always try to give preference to reads, because if we're reading data from disk, that usually means that somebody on the other end is waiting for it. Writes, because we're journaled, if we're writing data to disk, that's to clear out space in the journal, and there's not usually somebody waiting on that. We can tolerate a lot more latency on the write side. That also has a couple of other advantages that I'll mention in a second. The other thing we did in the I/O scheduler is we discovered that SSDs in particular changed their latency profiles quite a bit over time. And our suspicion is that has to do with things like garbage collection happening in the background, wear leveling happening in the background. And so we actually changed the behavior of the I/O scheduler so that we measure those latencies for each I/O. And when the latencies start getting high on a particular drive, then we'll start backing off how much we're pushing to that drive. We can let more data build up in the journal for a while and then push it out. And that reduces the load on the drive, and it more quickly gets the drive back into a state where it's servicing user I/O quickly. We did a lot of work on our journal, again, because we're pushing data so quickly through it. We needed to improve the way that we do locking. We needed to reduce the overhead of deciding when stuff goes out of the journal. And we made a lot of internal changes to help the journal improve the lifetime of the SSDs. And what we're doing there is a couple of things. One is that by having a very large journal that's in memory, we can reduce the number of times that we're writing to the SSD, and we can increase the average size of the writes. So write amplification, it can be a problem, and we can get rid of a lot of that, at least for mostly sequential I/O, by not just most sequential, but random if the SSD is grouping things together into a page, by just pushing more writes out at one time. And the other thing is that data that is frequently rewritten never leaves the journal. So we have superblocks, we have directories that are very busy. We may have databases may have things like write-ahead logs, which are being written in a very circular fashion. So all of the data goes into the log and then gets also written out into the database. And as long as that log fits in the journal, we never actually have to push it out, or at least not until the node we shut down the node for some reason. We can just keep replacing the data in DRAM, and those frequently written blocks never get written out to the flash and never use up any of the lifetime. Yes?
Back to the networking stack.
Yep.
You say that you implemented explicit congestion notification. Is that on the back end or on the client?
That's on the back end.
Okay. So interesting that you moved from InfiniBand on the back end
Yep.
to TCP over Ethernet. I mean,
Right.
why not use like Rocky or something like that? I would have guessed that that's the direction you would go in.
It's partly a matter of wanting to be as vendor agnostic as we can be.
Well, maybe your InfiniBand experience informed
Yes,
that?
yes, definitely. And partly it's that we looked at some of the RDMA type interfaces, and they don't work as well for this application as you might think.
That's surprising.
They
'cause I know
don't-
that,
they
like,
don't make as
Microsoft
big a
is using
difference.
them,
Yep.
quite a lot.
Right,
And-
for the SMB side of things.
Exactly. So they're using both Rocky and what's the other one?
iWarp?
Yeah, that's iWork. Thank you. Yes.
Yep,
Yeah. But you chose to just have it above layer 3.
for now.
Okay.
Yep.
Interesting.
Yeah, and all of
architectural choice.
all of this is below our RPC, so we may revisit that at some point in the
Oh,
future.
that's true, because you could just re-implement it without the
Right.
P stack. Okay.
Something else that I should mention, which also, I won't say it exactly informed our choice, but it was definitely a contributor. We use modified network drivers that allow us to do zero copy for our blocks in the network stack. So when we get an RPC response that has block data, that doesn't go into a socket where we need to copy it into the buffer. That the network driver actually says, oh, I have received something that looks like a block of data. I will put the header that has the RPC response onto the socket, and I will put the data directly into a data buffer and attach a pointer to that.
Okay, you've gone beyond me, but I appreciate it.
So basically, the advantage of RDMA is it avoids doing the big advantage of RDMA is avoids doing a copy.
So you're avoiding.
And we're doing that in a different way.
Way. Okay, thank you. That's
Sure.
better. That's more understandable. Thank you.
So some of the other examples of CPU and file system optimizations that we did, and a lot of these are quite general and don't really apply just to us. So many of these we pushed back into FreeBSD or are in the process of. One example is when we went to the 32 threads, we discovered that about 5% of our CPU time was spent doing what's called TLB invalidation. So when you have a page table, the CPU is caching the translations, and when you remove an entry from a page table, on most CPUs, you basically need to tell all of the other CPUs that are your peers to remove something from that table, from its cache. And that turned out to be really expensive. And by rewriting the algorithms that FreeBSD was using for that, we were able to reduce the cost of that by a factor of roughly 30 on our 32-core systems, which gave us back basically 5% of CPU that we could now use for actually doing I/O. For a similar reason, there are some instructions that Intel greatly improved the performance of in the Broadwell class of CPUs, and we rewrote some of the primitives like memory copy to use these new, not really new instructions, but instructions that now have lower latency than they used to. And again, that just gave us back more CPUs so we can run more of the file system. On sort of a different tact, when we moved to having a 256 gigabyte node and pushing data through it very quickly, the buffer cache management in FreeBSD turned out to be a bottleneck. There's basically a single daemon that goes through and it sort of cleans out buffers and makes them available for reuse. And one CPU core was not able to make them available for reuse quick enough for our other 31 cores. So we multi-threaded the buffer cache daemon, which means that under very heavy load, now we can simultaneously have multiple threads that are reclaiming memory to free it up for the file system
Might
effectively.
that be contributed into open source?
Yes, I'm not sure if that has yet, but it is definitely in progress.
Cool.
We also added interrupt balancing. You might think we build our own systems, we could just sort of statically balance the interrupts, but it turns out that the behavior on a node changes from moment to moment, especially when you have multiple interrupts from a single network adapter, which is pretty common so that you can have more than one core handling network. So you might have, say, 8 or 16 different interrupts that a network card can generate, and that's typically the selection between those is based on some sort of hashing of who's transmitting the data. And given our clustered nature, that means that if I switch from reading one file to reading another file that's set on one set of disks to a different set of disks, that's a different mix of those interrupts. And if our luck was bad, then we had a bunch of those interrupts that all wound up targeting the same CPU core. And so we now dynamically balance the interrupts out on the fly if we detect that too many are coming to one core. In the file system, some of the things we did, we have a fairly complex chunk of code that decides where to write data. And that takes into account things like where are other blocks for this file. There's advantages to trying to keep where you're writing close to other things, particularly on hard drives. We care about not spreading a file over too many disks because we don't want too many files to be affected in a recovery situation, things like that. So it's a pretty complex chunk of code, and it turned out that that was not a bottleneck on our hard disk-based systems, but it was on the flash-based. So we fixed that to cut down our CPU usage there by about a factor of 3, which turns out to be particularly important because that happens before things like ECC and the journal. So that's actually in the client latency path. Again, on the TLB, turns out to be a bottleneck in general, and so we redesigned data structures so we make more efficient use of the CPU. In places where we don't need to map data that's coming in from the network or from a disk into virtual memory, then we can avoid all of the memory management overhead altogether. We already did some of that, and now we do that in more places. So there's many more places now where we can just read a block from disk, land it in physical memory directly, shove that physical memory out a network interface without ever having to touch it. And then in the transaction manager, we had a fair amount of lock contention that became more evident as we had more threads that were simultaneously trying to commit transactions at the same time, and being able to do that much more quickly because our RPCs complete more quickly because the flash is faster than disks. So